Thus far in our conversation about forces, we've always been talking about balanced forces, things that are moving with a constant velocity or things that are just at rest. And every time we had something that was pushing us to the left, there was an equal amount of force pushing us to the right, or however much force is pulling us down, there was an equal amount of force pushing us up. But that's not always very realistic. There are many situations where we may have something that is pulling us to the right more than is pulling us to the left. And if we want, we can actually draw one of those little situations in a nice little force diagram right here in the corner. So let's pretend that we have an object sitting on a horizontal surface, so that the normal force and the force of gravity are equal. And let's pretend like we apply a force to that object, and it's going to slide across maybe this little tabletop, and the amount of force that we apply to it is much, much larger than the amount of force that is exerted by friction. Now, if we wanted to talk about the fact that the applied force is larger than the force of friction and how much larger it is, we would call that an unbalanced force. So an unbalanced force is the amount of force that is not canceled out by other forces. We can show that on this diagram right here. If we look at the force of friction and we try to kind of mentally lay it on top of the applied force, I think our force of friction would probably go out to about there. So this is the amount of our applied force that is canceled out by the force of friction. The rest of this, however, is not canceled out, and so this is the unbalanced force. Now, we are not always going to call it unbalanced force, and most textbooks don't call it an unbalanced force. In fact, most of the time it's called the net force. So net force is really just a fancy, well, let's see if I can spell the word fancy right, fancy name for the unbalanced force. So those are synonymous. You'll hear me in class use unbalanced force and net force. We're really referring to the same thing. We're referring to how much more force this applied force is exerting compared to maybe like the force of friction, or maybe how much the normal force is exerting, or how much more the normal force is exerting than maybe the force of gravity if we're heading in an elevator or something like that. Now, one thing to know is that the net force never, ever, ever goes on a force diagram. If you look at our little example up at the top, I can certainly point out to you the unbalanced force. It's this bolded area, right, on the applied force, but it doesn't get its own arrow. It doesn't get to have its own little vector on there, and that's a big mistake that a lot of new physics students will make, is they'll try to put, all the different names of the forces onto their force diagram, and then they add on another arrow to represent their net force, and that's not going to happen. Okay, so never, ever, ever include the net force on a force diagram. Now let's move on to Newton's second law. So we derived this out of your lab, if you remember. And what we got out of your lab is we got a nice little y equals mx plus b equation. And on our y-axis was acceleration. Now we figured out that the slope of our line was the same as our unbalanced force. So we are going to say that it is the same as our net force. And then we also saw that on our x-axis we had to have 1 over mass. So if we wanted to write this as an equation, we could write this equation for the graph that you got out of your lab as acceleration equals F net over m. This is Newton's second law, right? We wrote it last unit. Acceleration is directly proportional to the net force and inversely proportional to the mass. And this is going to be a hugely important equation for us. This equation is what the rest of this unit is built upon, so we need to memorize it. However, we're not just going to see it in that written that way every single time. It's not always going to say acceleration equals. We write a lot of force equations. And so last unit, we would be writing all of these force equations, and since the forces were balanced, they would always end up equaling 0, right? So we could sum the forces in the x direction, they equaled 0. We could sum the forces in the y direction, they would equal 0. That is not the case this unit. This unit, we're hoping that when we sum these forces, we end up getting some kind of unbalanced force. We end up getting a net force. And so because we have a net force, our force equation is no longer going to equal 0. Instead, it is going to equal something else. And the something else that it will equal is just another way to express Newton's second law. So rather than saying A equals something, we could rearrange this and say F net equals something, and that F net would equal MA. Now this is going to be useful for us because that means that when we write all of our net force equations, we're going to say that they are equal to MA instead of 0, which means that we don't have to change anything that we did from the previous unit to this unit. We still are going to draw a force diagram. We still are going to write a net force equation. And now the only thing that changes is that instead of that net force equation equaling 0, it now equals MA. Okay? And just remember, F net equals MA. It's not really anything different. It's just another way to write acceleration equals F net over M. Now before we end this lecture, there's one last thing that I would like to note. The mass part of F net equals MA. That mass part of this equation really refers to the mass of the system. So we're talking about anything that is moving at the same acceleration. As long as things are tied together and they are forced to move at the same acceleration, then we need to count all of that mass as the M in our F net equals MA. This is not going to be that noticeable unless we have problems that look like what we saw in your lab, which is called a modified Atwood machine, where we've got two boxes and they're tied together and maybe one of them's hanging over a table, one of them's sitting on a tabletop. Problems like that are going to really expose the fact that the mass part of F net equals MA needs to refer to the mass of the system, which is the mass of everything that's moving at the same acceleration.